This particular video today, guys, is going to deviate a little bit from what I've been doing in the past. So we've been doing a lot of fiberglassing work, structural work for my hull extension, but we've got to start thinking about the electrical and all of the other things we've got to do in the future. So we're going to start having a look at the electrical design that I'm going to be using in my boat. Now, when I say electrical design, I'm talking about ELV circuits. I'm not going to be talking about LV circuits. The legal requirements here in Australia are very, very clear. You must be a licensed electrician to work on LV circuits. And for that reason, I'm not even going to talk about LV circuits. I'm just going to be going into the 12 volt DC ELV circuits for now, and then I'll go into some of the other things later on. I'm licensed here in Australia to do, my licenses are unrestricted cabling licenses. I can do everything from these tiny little wires, fibre optic cabling, coax cabling, all of those different things. So I don't have any problems with that. My trade background is electronics way back in the 1980s when you used to repair things to component level. But anyway, so I've got a list here of some of the things that I'm going to be doing in the future. I'm going to put that in the description of the video down below. So if you're interested in this sort of stuff, make sure you have a look. Some of the things, just a few things that are on this list, we're going to be having a look at clean power. So clean power, very, very important in pretty much any industry these days. So especially when we're talking about very sensitive electronic equipment, we need to make sure that the DC voltage is ripple free, we don't have any noise on top of it, there's no white noise or anything else that's going to be generated within our screens on our chart plotters or fish finders from the power. We're not going to get voltage drops or voltage spikes that are going to create problems for us. We need clean power. So that's what clean power is. We're going to have a look at mechanical protection for our cabling systems, very important. Conduits and basically systems that are there to protect the cables from physical damage. It might be movement in a caravan or a four-wheel drive in a boat, whatever, but mechanical protection for our cables is extremely important. We're going to be looking at the wire size, how we create the wire size. We're going to be having a look at the fuses, why fuses are important, and we're going to try and do some practical experiments to pop those fuses and to burn some cables and see what we can do. Try and make it a little bit interesting. So that's what we've got coming up in the future anyway. Hope you enjoy it. Oh, the other thing that we're going to do is we're going to use software. We're going to use SmartDraw for our system design. So that gives us the opportunity to sit down and actually create a design. And within that design, we will take everything into consideration: our fuse sizes, our cable sizes, the length of the cables, the overall length from our load and back, and all of those different scenarios that we need to consider when we're doing these installations. So, hope you enjoy it. This video, a little bit of a practical one about DC voltage measurement and AC current, not AC current measurement, DC current measurement. Hope you get something from it and hope you enjoy it. Okay, so essentially what I've got here, guys, is I've set up what I'm going to refer to as some mock circuits. What I mean by that is I've basically got some circuits set up there with fuse boxes, my bus bar, negative bus bar sitting there. I've got a switch box there, so I didn't want to recess it into the board itself. So what I've effectively done is put it on an IP55 junction box for no other reason than to stand it off of the backing plate itself. I've got some nylon glands there. So typically if I was going to put anything into a junction box on a boat, I would want to make sure that I seal it up properly and make sure it's watertight and everything else. So what I do is use these nylon glands. So that's them there. Essentially, you can get them in different sizes. They're 16mm nylon glands, those two there. And what they do is they've got rubber seals on them, so when you drill the hole into the box, you can seal them up, and then you tighten it down over the wires themselves, and it seals it all off. I have done some heat shrinking on my wires coming into my negative bus bar and into my fuse box. Basically for show and tell, I guess, more than anything else. We've got all of our wires coming out of the fuse box going into the switches, and then from the switches out to our different circuits. I've got a water pump here, I've got a depth sounder sitting there, GPS, I've got a bilge pump, I've got a fridge, little fridge, and I've got a kettle. I've also got my normal multimeters and everything. So I've got, we always use the Fluke multimeters. I've used these pretty much since I've ever started when I was doing my apprenticeship. So this one here is a Fluke 115. We'll have a look at that a little bit later, maybe not in this video so much. We will be measuring voltages, and then we've got a clamp meter. So we're going to be using this clamp meter to measure our current. Basically, we're going to have a little bit of a play with the current and the settings and work out what each of these devices, how much current each of these devices draw, and what the maximum load is when everything's switched on. We can have a little bit of fun with it. We can do some fault finding, work out why certain things won't work. Righto, so we might as well start hooking up some power to this thing, eh? I've just got nothing fancy down here. I've got a lead acid battery there, and I've got a lithium ion phosphate LiFePO 4 battery sitting there as well. I'm just going to use the lead acid battery for this particular scenario once we get it all up and running, and we'll have a bit of a play. We'll measure some voltages, and we'll make it do some stupid stuff. So the very first thing that I want to do here is I want to measure our DC voltages to make sure that we've got power to these circuits. It'd be pretty easy to work it out straight up by trying to flip these switches and see if anything works, and nothing works. So what we've got to do, or what I want to do, is essentially measure our DC voltage and find out what's going on, what's happening. Have I got a switch off? Have I got a blown fuse of a circuit breaker, whatever. This is sort of a practical way of trying to fault find something if you've got something go wrong on your circuits. So essentially, exactly as I was saying just a little bit earlier, is what I want to do is I want to measure a DC voltage. So we go across from, that's voltage AC there, we go from the AC across to the DC, and that's where we want to be. So we want to measure our DC voltage, and then we've got our negative, whoa Robbie, whoa, careful. We got our negative and positive leads. Doesn't really matter in this case whether you get them around the wrong way, because what you will essentially get is a negative reading if you've got a reverse polarity. So it's not really a problem with these style of multimeters, most of them anyway. Something that is really good about these two is you can get little connections for them, and what I can do is slip a little alligator clip over the top of it, and then I don't have to be holding it in position. So the first thing that I want to do is work out what's going on. Nothing's working. Why isn't any of it working? Obviously I've set something up, but what we want to do is put our negative probe on our negative bus bar. So I'll just clip it up there for now. Makes it nice and easy, just sits there, no problems at all. And I go across to here. So we can start by having a look at our fuses. Now if I go to these fuses, what we notice is I've got 0 volts DC on there. Why have I got no voltage at this point? Let's go down to our circuit breaker. So this is the very first circuit breaker in the circuit itself. This is the one that sort of comes from the battery, and it comes up to the fuse box. So we're protecting the wire from the battery to the fuse box, and then we're protecting all the other wires and all the other sub circuits via this fuse box here. They're different ratings, as you can see there. I've got some 5 amp fuses and I've got some 10 amp fuses for the different components that we've got set up here, and there's a reason for that, and we'll have a look at that a little bit later as well. So essentially what we've got is 0 volts on this side of the circuit breaker. Yeah, 0 volts on that side of the circuit breaker. And then I want to have a look on the other side of the circuit breaker. What have I got? 12.46 volts. So what does that mean? It means that we've got an open circuit. When we flick a switch, what we're doing is we're closing contacts. So assume my crazy arms here are a switch for a minute or a piece of wire, and if we've got an open circuit like that, the voltage can't flow between there and there. What happens is when we've got a circuit breaker or a switch or a fuse or anything like that, we are closing the circuit. So we're effectively closing the circuit just like that. I'm going to grab a piece of wire. Start talking about switches, circuit breakers, fuses, and we talk about open circuits and short circuits and all of that sort of stuff. Then what we're talking about is that is an open circuit with big air gap. the two wires are not touching. Obviously when we touch that, now we've got a short circuit. So all the switch does is basically goes open circuit, short circuit, open circuit, short circuit, open circuit, short circuit. When you've got your short circuit, you've got continuity, and you'll have current flow. As long as you've got devices on there, obviously, you'll get current flow. Okay? And you've got a closed circuit. Short circuit, closed circuit. I've just realised that I've missed a very important part here, and it is critical to what I'm trying to explain right now. So what is the difference between voltage and current? So the voltage is the potential difference between two parts. So when we talk about the potential difference, we're looking at the potential difference from our positive rail, or let's say our positive rail is here, to our negative rail. So we know that our negative rail should be sitting at 0 volts, and our positive rail is going to be sitting at whatever it's going to be, 12 volts, 24 volts, 36 volts, whatever. In this case, it's 12 volts DC. So that's the potential difference between those 2 points, 12 volts DC. Now what we want to do, if we're measuring 12 volts across this switch here, or this circuit breaker, then that means that we've got an open circuit. So it's not actually closed. If we fix that, so let's have a look for it. So I'll grab my trusty little Fluke multimeter here again. We switch it to our DC setting again. We come back here, and we know that this wire here, just here, is coming into the circuit breaker, and it's our very first connection. So we put the multimeter on there, and we've got 12 volts DC, 12.46 volts. Now if we go to the other side of that circuit breaker and we measure that point there, what are we going to see? 0 volts. So why are we seeing 0 volts? Pretty much exactly as I was explaining there before. We've got a switch that is currently open circuit. Now what we want to do is we want to short circuit that switch, close it up so that we've got continuity through the circuit breaker itself. If it's open, we're going to get 12 volts voltage drop, or potential difference across there, I should say. And when we close it, so make sure they're all off, flip that on. Okay, let me just check that again. So currently we've got our 0 volts DC. Yeah, 0 volts DC on that terminal of the circuit breaker. Flick it on. I'm hoping that you're going to see 12 volts then, 12.46 volts. So that means that that's now working. Flick it off again. Should disappear. Yep, off, on. From there, what we probably want to have a look at, that's the basics of measuring DC voltages anyway. Now I can measure between that point, our negative rail there, or I can measure to our fuses or to our devices, anywhere across our circuit here. And basically what we're looking for is our 12 volts DC. We want to see the full rail at those devices. You may get a little bit of voltage drop across the wiring systems or your cabling systems, and that, depending on the size of the conductor and what your load is something that we're going to get right into in another video. We're going to talk about the cable and wire sizes and everything else, and why it's important. I'm going to do a little bit of an experiment here very, very shortly to show you that as well. But that's it. So we can measure all over that circuit to work out our voltages, our potential difference. Now, what I'm going to do is I'm going to grab my clamp meter here. So the clamp meter is very, very easy to use. All we want to do, in this case, what we want to be doing is measuring a DC current. The DC current is the number of electrons going past one point in the circuit. So on that there, what we've got is, I've set it to 40 amps DC on the 40 amp range. And you'll notice straight up what we've got is an offset. So that offset there is, what is that, 400 odd milliamps, between 400 and 500 milliamps, and that's going to any reading that we try and make is going to be off. So what we need to do is zero that out, and to zero that out we hit that relative button there, and that pretty close to it. So that's, oh, let's zero there. Fluctuates a little bit, not too much. So what I've done is I've just basically set up my clamp meter. It clamps around the wire itself. So I've got it coming around the positive lead that comes into the bottom of the fuse box, and what we're going to be able to do from that is measure the current when we start switching these circuits on. So what I'll do is one at a time, I'll switch the circuits on and we'll have a look at, first off we'll sort of switch this pump on. We'll have a look at that, then we'll play around with the Garmin there, the fish finder, and our bilge pump as well. Alright, so right now we've got what, 10 milliamps. Let me do that again. Whoops. Bring that back to 0. Okay, and let's turn this on. So that's our pump. Alright, that's the water pump, and you can see that's sitting at 1.45 amps. Somewhere thereabouts anyway, fluctuating a little bit. Okay, now let's turn some of these other devices on. Oops, didn't hold it long enough. So we've turned on our Garmin here. Current has come up a bit, so it's drawing more current. Let me turn that off. So you'll see that drop down. Okay. Ugh. Turn it back on. 2 amps. See how it goes. That's something that I should probably explain as well. Something that a lot of different devices do is they have what they call an inrush current. So basically, and that's because of the inbuilt circuitry or whatever is inside of these devices, and it'll all be different. They'll all be different. So when we first turn our pump on, I want you to see how our current is affected. So what we will hopefully see is you'll see an inrush current where it goes right up for a split second, and then it comes down and it settles itself down and it sits at its normal operating load current. All right, so let's have a look. Hopefully, there you go. Turn him off, turn him on. We might have to do that a little bit later. Not a real good example of that one right now, but it will definitely be more apparent when we switch the fridge on, for example, and even the kettle. That kettle draws quite a bit of current. So that's a 150 watt kettle, so it draws a fair bit of current. So you'll notice too that our DC voltage is starting to drop. I think my battery is probably needs a bit of a charge. They have been sitting out of the boat for a couple of years now, and they need a bit of attention. So that's my fault. Our sounder is on. Something that I want to have a look at as well is when we, how do I get into the display of this thing again? That's it. So our backlight. So you'll see on the backlight, oops, hit the yes. See, as I turn the backlight up and down, but I want you to have a look at what happens when we do that. So if we go across, so that's quite dark at the moment, darker. That's all that's drawing right now is about 250 milliamps, and if I start to turn it up, you'll see up to 300, almost 500 milliamps. Keep going. Alright, we're at max now, 100% backlight. So the brighter the light that you've got on your depth sounder, or any device for that matter, the more current it's going to draw, more battery consumption it's going to need, or the more power consumption it's going to need, and it's going to use your battery up a little bit faster. There we go. Sitting there idle at the moment, basically 100% backlit, and it's at 600 milliamps. Let's just call it 600 milliamps. And then again, turn our pump on. There, you saw the inrush current there. Let's just let that settle for a bit. Get the inrush current, push up, and then it settles down a little bit. There we go. And then we've got, oh yeah, just making sure I had my bilge pump switched on there for a second. So what I've got is a float switch set up on the bilge pump. You know, when I was talking about switches before, that's all this is essentially a switch. Power comes down through the switch and goes to our positive lead of the pump itself. So when we turn that pump on, so obviously when the base is sitting there, hopefully there's no water in the bilge or whatever, and it's all good. If you start to get a wave over the bow or something like that, pump's going to start up and start to let's have a look at how much current that thing draws. So I've still got the sounder on at the moment, so that's just sitting there. Let's have a look at how much this. So there you go. What's that? About 500 milliamps, half an amp or something like that. But keep in mind that current that's drawing currently is under no load condition. And what I mean by that is there's no water going through it. So the impeller's just sitting there freely spinning with no, what would you call it? Like, well, no load on the impeller itself. So it's just free spinning. Not drawing much current at all. Pretty simple. So what I'm going to do is I think it might be a good idea to hook up this kettle over here. Let's hook that up and see what that does. That's going to make a big difference. Now, remember what I said before about my battery? Let's have a look at something. First thing, so the kettle's on. Notice that my battery voltage has dropped down significantly, but have a look at how much current that is actually drawing. So that's drawing 9.63 amps, up and down a little bit there. So it's a fair bit of current, and that's battery is struggling a little bit. So if I go, and that's actually on that point there, so the bottom of our fuse box. The very first point, well, not the very first point, the very first point is down here. Whoops. Our circuit breaker there. And if we come up here, 10.96 volts. So 11 volts to 10.96, we got a voltage drop there about 40 millivolts. But we've got, there you go, 9.6 amps. So that's a reasonable amount of current. That's going to take a little while for that kettle to boil, but we don't really want it to boil. That's not the intent of what I want to show you here. So what I want to do is basically set this up so that I've got wire that's too small for the circuit, and then we're going to have a look at what that does. Okay, so let's have a look at that. So what I've just done is I've basically just disconnected the standard leads that go to that kettle over there, and I've replaced it with some alligator clips or alligator leads, nice little thin leads. So what I want to be able to do here is see, oh, I've also got a little thermometer there. So that thermometer is going to show us whether or not there's any heat that's going to be in these wires, because we're going to be drawing a fair bit of current through those wires. Well, 10 amps, it's not a huge amount of current, but it's an example of what happens if you've got a wire that's too small for the load that you're supplying. So we're going to be drawing 10 amps through a tiny little wire. Let's have a look at it. Let's see what it does. Okay, what have I got to switch on? I think I've just, kettle is switched off. Alright, let's switch it on. Ooh, so we're currently drawing 6 amps. That's not a lot. That's dropped a little bit already. Our DC voltage is sitting at 11.46. We'll have a look at this, guys. Already, that temperature of this wire has already started to go up. So I've just got that wire wrapped around that thermometer lead there. So we're at 60 degrees, that's in Celsius by the way, see, 60 degrees Celsius, and it's still climbing. So that's going to be quite hot to touch there in a second. Still climbing, still climbing. We're still at 6 amps, 12 volts DC. Wow, I don't know how accurate this thing is, but this should start to smoke any second now, because normally PVC has a melting point of about 85 degrees Celsius. Let's see what it does. Our kettle is still on. Hasn't dropped off yet. Oh man, that's getting warm. That's getting hot. You can see that red wire there. Yeah, it's starting to smoke now. Starting to get a bit of smoke out of that wire. It's escaping. The smoke's escaping. Yeah, that's an old joke. Yeah, there we go. Not sure if you're going to be able to see that very well, but oh, it's starting to go around. Yep. We're at well over 100 degrees Celsius now. That is going to be hot. So you can imagine if you've got that, an undersized wire or a cable of any sort in your caravan, your boat, your four-wheel drive, whatever, you hook up a big load to it, you start drawing way too much current, it's going to get very hot. Once it gets hot enough, that insulation is going to basically disappear. There we go. You can see it where it's wrapped around the thermometer itself is where it's smoking the most. We've got plenty of smoke coming out of there now. That's going to be pretty hot. So that proves a point, guys. The point that I was trying to prove is pretty simple. You must set up the right wire or the right cable for the load that you've got at the other end of it. If your wire's too small, you're going to have a problem like this. There we go, starting to melt. Oop, starting to go. What I want to do is prove something else to you, and it will in a second. So you can see if we get right up close there, have a look at what it's doing now. Yeah, I should probably have a mask on now. This is starting to suck in that smoke. So that's only at 5.5 amps with a tiny little wire on there, and it's all, the insulation on that cable is starting to melt. So what happens then is if you've got a cable, apart from the fact that if you've got any combustible materials near that, then that can catch fire. But what it'll do is that insulation will melt, all of that insulation around the copper conductor itself will melt, it'll become non-existent, and then you can potentially get short circuits between your positive and your negative, causing arcs and sparks and everything else, and it becomes a serious safety issue. So we're well and truly, it's almost like it's going into thermal runaway now. Our voltage has dropped down a little bit more. Yeah, she's getting hotter and hotter. It's still going up. I'm going to flick that off in a second. There we go. So I've just flicked that off. Let that go. Watch the temperature come straight down already. It's already coming down very rapidly. And that's because it's got no more current flowing through the circuit. No more current flowing through the conductor or that wire. So it's starting to cool itself down. Albeit way too late. Our voltage has come back up. Our current on our current meter there has dropped off. And that's essentially what we've got. So I hope that makes sense to what I was trying to prove. Again, was that if we've got a wire connected to a load and the wire is too small, then you could potentially have this issue. Very, very important to get those wire calculations right. I hope that makes sense to you guys. I'm just trying to sort of prove something there. Starting to come back around. Don't think for a minute that if you've got microwave ovens, and you can get 12-volt microwave ovens now, you've got your kettles, your toasters, your pie warmers are probably a classic example too, because they've got an internal heating element, so that heating element's going to draw quite a bit of current, probably similar loads to this, 150 watts, 200 watts, maybe a bit more. You don't want these tiny little wires being connected to them. You're going to have a problem. So I didn't have that kettle on for very long. Water didn't even boil, so I didn't allow it to go that long. How bad do you think this cable is going to be, and this wire? Let's have a close-up. Let's have a squeeze at this. Have a look at this. There you go. So that's it there. So the PVC or the insulation is basically just a molten mess right now. Not much left of it. Again, I know I'm harping on this a little bit, but again, oh actually, oh no, I thought you could see, yeah, Yeah, so I know I'm harping on this a little bit, but again, the whole intent of just doing that little thing, that little exercise there, is to show you what can happen if you've got a wire that's too small for the load. So if you're drawing too much current through that wire that it's not capable of handling, then that's essentially what you're going to get. Or even worse, there's not much left of that insulation now. That would certainly burn off or melt to the point where the conductor would be open, and if you've got another cable wire sitting next to it, potential to short circuit, create some problems. Anything near it, maybe it can draw an arc or create a fire. Even the heat from that is probably potentially enough to cause a fire. And it's not just the arcing and sparking, it's the heat. So one of the industries that I work in very, very closely is fire protection, in the fire protection industry within passive fire. And what happens is we have to anyway, long story short, I'm waffling on here a little bit. What we've got to be careful of is the amount of heat that can be generated from one side of a firewall to the other side, and because of the reason that if it gets to a certain temperature, it can ignite combustible materials. So we don't want that, especially not in a boat when you're 100 nautical mile out to sea or even further. Whatever, you want all of these things to be right. You don't want it you don't want it in your caravan. I know there have been a bunch of caravan fires. Well, I've heard about a bunch of caravan fires that have been caused by similar sort of scenarios. So just be careful, guys. Just be very, very mindful that your wire, your cable selection, cable is multiple wires contained within the same insulation. So your wire size is critical. It's really important to get that right. Don't undersize the wires just because it's cheaper, because obviously wires are made of copper conductor, and it can get very, very expensive to get into some of those bigger wires. Make sure you size it properly. Don't take shortcuts. Don't go with the cheap alternatives or anything else. Make sure you spend that money and get it right. I hope I hope you found that interesting. Anyway, I thought it was pretty cool. I didn't know. I had never done anything like that before. I've certainly seen some wires that have been undersized and had some issues, but that's a pretty good example, I think. Anyway, hope you enjoyed that. Have a look at the list that I've got in the description and see if that's going to benefit you in any way, and I'll check you out in the next one.